Okay, so I think we can start.
Yeah,
So
sure.
good morning, everyone. This is the second tutorial that you guys have on linear algebra by Arjun. So Arjun, you can start.
Yeah, bienvenue. Welcome, guys, to Linear Algebra class. So in this class, we will be like brushing up about like linear algebra skills, and we will also be talking about how it will be helpful in real time when you learn about machine learning. So it will be a good experience for you to understand the intuitive concept of linear algebra. So whenever you learn about machine learning concepts, so that always helps you. On top of that, like we will be like seeing some Python implementations with linear algebra, so that this is also helps you in programming and then like assignments, all those stuff. So if you already have been like knowledgeable about linear algebra and then like all Python implementation and then like implement in machine learning stuff, then like feel free to skip this lecture, but remaining like I've made sure like it will be useful for you in all aspects. So like let's start with like a traditional approach. So generally like we have like two equation, like 2x plus 3y equal to 8, and then like 3x plus 2y equal to 7. So when we have two equation, when we want to get x and y, we obviously like multiply the equation with a number and then like make sure it's kind of common, and then like we cancel out each other, and then we'll get y equal to 2 and then x equal to 1, and then we can always substitute it back in the same equation and check whether the given equation is right. So for two unknowns, it's always easy, like we can do it to some extent. And let's take an example of three equations. So we have x, y, z. So obviously this is kind of slightly a complicated case, because first you want to solve two equations and then have one sub equation and then add up to this, and then like the things makes it even more complex. So similarly, like as the number of unknowns increases, let's take if 3 unknowns is there, but it's kind of not very easy to solve compared to 2. If it is a 4 unknown, 5 unknown, or 10 unknown, so it's really complex to solve those kinds of problems. So we will see like how we can solve better. So before that, let's go into some basic terminologies in linear algebra, so that you will have a good understanding of like what's going to come next. So like first thing is like a scalar. So obviously like it's just a single number. So in this example, you see 11 is a scalar, like 12, 50, 100, like 2 or 1 or like 3. So any single number is always represented as a scalar. And a vector is like there would be two vectors. So one is a row vector and another one is a column vector. So here is the two examples that you can see. So that you can see the shape, this is like 1 cross 3. So that is 1 row, 3 columns. So here you will have 3 rows and 1 column. So matrix is a combination of rows and column vectors. So you see like here you have 2 rows and then 3 columns. So the shape is like 2, 3. And in another next concept is like a tensor. So it's not a scary word, it's just like stacking up of matrices on top of each other. So you obviously know this is a matrix. So this is a three-dimensional matrix. So that is a tensor. So here you have like people say in another terminologies, like if it is tensor 0, then it's a scalar. If it is 1, then it's a vector. Then if it is 2, then it's a matrix. If it is a 3 tensor, then it's a 3 tensor. If it is n, then people call like if it is 4 means like 4 tensor. Like so there is another terminology people kind of use it in machine learning also. So let's see like what is a row vector and the column vector. And so this is like, so it is a 1 cross. So 1 row, you have multiple columns, then it is a row vector. And for the column vector, it's like multiple rows and 1 columns. So you can always go back and forth between like A transpose and A. So you can always go back and forth between row and column vector. So this is what like basic till now what we see was like what is a scalar, vector, and matrix and a tensor. So this tutorial would be like a kind of a practical assignment that you will also be trying with me together. So what I would suggest, like I will give a quick intro about what is Google Colab and how you can use it. So generally, even if you have if you don't have a big computation in your laptop and you can't run anything, any big programs or something, so Google Colab is like a cloud platform where you can run the IPython notebook or like Python codes, not based upon your local system computer hardware, based upon the cloud hardware. Like, and if you see like change runtime, you have like GPUs and TPUs that you can use, so that whenever you work in some projects, so this always helps you, and so that your system doesn't get slows up. So you can't edit in this notebook. So what you can do is like, I will share this link with you in the Zoom. So you can go to File and then save a copy in Drive. So what happens is like, it creates a copy of this notebook, and if you're not logged in to your Google account, so it might prompt you for like to log into your Google account. So I will kind of like give you 1 or 2 minutes so that you can quickly make a copy. And if you have any questions or like if you have any difficulty, feel free to ping the message. And then you can always rename as like version 2 or like, and then like you can run this notebook, and then you can edit or like whatever comments you want to make, and then like whatever additional notes or like, or feel free to like make your own notebook and then like work on it, so that it will always be helpful in the upcoming days. Okay, I believe like you might have taken a copy. So it's like, let's start with like practical implementation. So it will be good like if you even play with the numbers. So whatever we learn theoretically, at the same time, we will learn how to implement in Python. So if you are new to Python, or like if you want to slightly upskill in terms of linear algebra skills, so this comes into better help for you guys. Okay, I don't see any chat messages, so it seems things are going good. So the first line is like all import functions. So we will be importing NumPy and then some linear algebra and statistics libraries. So here, like we will be defining a row vector. So to define a row vector, you have to use np.array. That is a NumPy. So we will be using the short form of NumPy, and np.array of we can define a row vector here. And just to print and see like what's the number you have, you can always use the print command. And then like if you want to know the shape of the row vector or a column vector, so the inbuilt function is to use the shape. So this shape comes very useful like whenever you're coding, like whenever you're handling the matrix, and then like you want to know what shape of the matrix that you are playing with. So this shape always comes into play. So similarly, the next is like a column vector. So you can always use a transpose to just swap between a row and a column vector. And similarly, the same thing is for like, you can always print and see what's the variable, and then like column vector dot shape gives you like, this is a 3,1. So that is 3 rows and 1 columns, which is the column vector. So till now we have seen what is a scalar vector and how to define it. So next, what we'll be seeing is matrix. So let's take, when we take this flower image, we obviously see that as a flower, but the computer doesn't see it like that. So computer inputs would be like RGB. So that's a pixels. Since there would be 3 channels, R for red, G for green, and then B for blue. So this is a 3-dimensional three-dimensional tensor. So that's what we have seen. So it will be like kind of in this format. So first one would be like R, second one would be a G, third one would be the RGB like format. And so similarly, like whatever we see as a processed one, so the computer doesn't see everything as a numbers and values. So similarly, like if you have tables, so everything would be converted into matrix. If you have images, everything would be again converted into matrix for processing. And again, if you have text data, or like if you have like some sentence or sentimental analysis classification, or like whatever projects you do on text also, again, every text would be converted into an encoding of a number, and then those number would be processed for building a model, all those stuff. So obviously, like we will make use of matrix to make all the computations and things even more better. So this is how we will be defining a matrix. So again, the same thing, like you define a variable and then np.array of, and then like this is the first row, this is the second row, this is the third row. So similarly, we have 3 columns. So you print a matrix variable, and then like you get this shape. And similarly, like you can define another matrix like with another variable. So this is how you can define matrix of your desired shapes or size or like whatever number you want. So let's see like what is a scalar matrix multiplication. So here the matrix value is like A is like always 1 1 1 3 cross 3, and then like when I multiplied with 10, so it's like the values are became like 10 10 10 or everywhere. So if I just print it with multiplied with 5, yeah, so everything is like 5 5 5. So similarly, you can do the matrix addition. So you just have to use the plus operator, and then like here you see like 1 1 1 1 1 1 1 1 1. Similarly, like 2 4 6. So 2 plus 1 3, 4 plus 1 5, 6 plus 1 7. So that's what the output is. So every element position should be the same while you're doing the addition. At the same time, the shape of the matrix should be same. Let's take if A is 3 cross 3, then B should also be 3 cross 3 in order to do the addition. And so this is a transpose operator. Like you can use dot T in Python to always interchange between the rows and columns. So you can see here you have like 3 rows and then 4 columns. So and then like you can see that has been, since we are using an inbuilt function of dot T, you can see like now it has been converted into like 4 rows and 3 columns. So this kind of like transposing a matrix and then like multiplication, addition. So all these things would be helpful for you in the assignments, because when you ask you to like do it from the scratch, like you have to do all the multiplication and addition. So this comes handy during that time too. So next would be like the matrix multiplication. So for that you have to use np dot. So this is our classic matrix multiplication with row into column, the first row, the first column. So that's what the value holds here, and the like first row and the second column. So that's what the value will hold here. So similarly, second row, first column, second row, second column. So and then you add all those values to create a dot product value. So this is the dot product. So while matrix multiplication, we have to take care of another thing is like the shapes should be compatible. So here you can see like it's 2 3. So then this shapes cannot be multiplied. So that's where you will throw an error like the shapes are not mismatched. So whenever you getting this error while you're practically implementing few programs or something, then if you get some error, then you know like, okay, this shape is not good, then you should rearrange or transpose or make it in a proper way so that you can do matrix multiplication. So this is a matrix vector multiplication. So it's similarly like same as like matrix dot of. So you can use np dot of matrix comma vector. You can also do that, or you can also do it in this way. So here you have like the shapes are should match like with this and this. So then the output would be 4 and 1. So that's what the expected output is. So this is what we have learned in our high schools, are like how to do the multiplication. So this is how we implement in Python also. So I will give you like so till now we have seen how to define a variable, define a matrix, define a vector, define a scalar, and then like scalar matrix multiplication, matrix vector matrix multiplication. So I think you might have taken a copy. So I would suggest like I will give you 1 minute of time. Like you can just use the variables are matrix A and matrix B. So try to find the dot product of A and B and B and A, and whatever you infer, like whether it's same or like different, please add the results in the comment so that let's see like why it's happening. So I'll give you kind of take a minute. So it's like you already have the codes available. So if you can't solve it in a minute, like I can give you the answers, but I highly encourage you to solve and let me know like what results you infer. So you can use, already we have declared matrix A and matrix B. So you can just use the same variable for the dot product. Yeah, exactly. B and A incompatible. Can you check your implementation again, because the shape of matrix A and matrix B is like it is like 3,3, so it should not be a okay. Like let me proceed. I think we got out of. So whenever you're getting this error, you can always print the shape. So it's like somewhere like it's 3,2. Okay, so it's like here it's what happening like. Okay, so you can again like declare this variable, because here the variable has already been updated. So you can so here you can see like the product of A and B is not equal to product of B and A. Or else I would suggest like you can change this variable name and then like try to run all. So please fix the variable name here and then try to run all, so that the whole variable would be like updated. Okay, the best thing is like you can always take this variable, because we'll be using this for like other problems. So it's like just declare any 3 cross 3 variable and then like try to run it. So yeah, so here you can see like generally in multiplication we can always multiply 3 into 4, or which all 3 into 5, which always gives 15, and similarly like 5 into 3 always gives 15. But in matrix the problem would be like you can't always like interchange the matrix multiplication, but because like it gives you a different result. So next we will see like another interesting thing, like so why, if you can't define always a number, so we can always use np.random. So this helps you, like if you define the shape, then it always helps you to, like if you want a 3,2 matrix, then you can just define like this, and then like a random number would be printed. So this helps you to, like when you work with neural network or something, when you just want to start with a random weight, or like in any case, it will be really helpful, like to implement from things from the scratch. So if you use np.random.rand, there will be a problem, like if I run it again, so that if you can see like always the values will be changing. So if you want the code should be like always gives the same random number, so you have to set it as a seed, so which is like np.random.seed, and then like similarly I'm gonna define like 3x2 matrix, and we will be seeing like how it works. So you can see like 0.7713. So if how many times I run, it gives you the same result. So this is for the code reusability generally we use. So you will be seeing all those concepts like in the thing, like, but this is like a practical application you can always use for. So this is like storing a random variable in a matrix, and then like you can always print the shape, and then you can see like a type of random matrix, and it's always a numpy, and then like in numpy array. So again, like this is a quick practice for you. Like we'll be seeing like associative and distributive property in implementation. So for that, like you can like define a matrix shape, matrix A, matrix B, and matrix C of 3, 3, 3, and then like you can try to compute it, and let me know like what do you infer, whether it's associative, or like whether it does also satisfy associative. So I can give you a quick 1 minute time so that you can implement it. So just to quickly help you, like, so this is how you can define a random matrix. So now you have A, B, and C. So try to solve going forward. And if you have any difficulty, or if you got the answer, like whether it's same or like different, so feel free to post it in the chat too. So you can take a 2 minutes of time, and then like try to implement these two things. So we have learned already how to do matrix multiplication, and then like matrix addition. So don't change this seed so that everybody will get the same answer. Okay, like I'll give you like last 30 seconds. Okay, not like we will solve it together. Okay, I think I will proceed. So here, like you have to use np dot of. So the first one should be the matrix A, and then like inside you can use np dot of b comma c. So similarly you can do the same thing for like print of np dot of. So here you have np dot of a comma b comma c. So you can see like you're getting the same matrix. So we obviously know like associative property of the matrix. So this is how you can implement it in Python. And similarly, you can again store it with a variable or all those stuff. Like however you would like to implement, you can always implement. So it is associative. Sorry, I need to use print. Okay, so similarly, you can do the same thing here, like here np dot of, and you can just use a plus b comma c. Okay, before that you have to declare it. And np dot of. So we want to do a comma c plus np dot of b comma c. So again, you can see like the shape of the matrix and then like the value of the matrix is the same. So this shows like again it's a matrix multiplication is again a distributive property. So till now, if you have any doubts or like if you want me to like quickly clarify anything, like feel free to like raise hands or like give it in the chat. Like I can quickly explain that to you. Okay, then let me move on to the next topic. So now let's see like some basic terminologies, so that will help you to understand like even some advanced concept in linear algebra. So here, what is the rank of the matrix? So if the matrix has zero determinant, then it is a singular value. So a singular value is like, just quickly see this example. You can always see like the first row is 2, 3, and then like it's 4, 6. So this shows like you can, if you multiply the first row with 2, you can always get 4 and then 6 similarly. So this is a non-singular, this is a singular matrix, and therefore you can't always find the determinant. So if you take the determinant quickly by 6 into 2, 12, minus 4 into 3, again it's 12. So it will always be 0 for a singular matrix. So similarly, the rank of the matrix of this A is 1. That's what they're trying to say. Like if you have two identical rows, in other words, this row is not a dependent of another row, then they are not dependent, and then the determinant is 0. So similarly, that goes for the column also. So then the rank means like the number of independent columns. So in this example, you have one independent column. But if you take this second example, so whatever you do, you can't always reproduce with one row with another row or one row with another column. So then this matrix is called a full rank matrix. And then again, this is a non-singular matrix. And all two rows on two columns are like linearly independent. But here it's not the case. Like this row is linearly dependent on the first row is linearly dependent on the second row. And it is a singular matrix. And the rank is 1. For this matrix, the rank is 2. So previously, I think we have seen the equation as like 2x plus 3y equal to 8, and similarly like 3x plus 2y equal to 7. And so what we will do is like we will try to solve it using a matrix way. And let's see like how how to do it. So what I'm doing is like, let's take the coefficient of x, the coefficient of y has been like 2, 3, and similarly the coefficient of x is 3, the coefficient of y is 2. So let's make it as a matrix. And similarly, like 8 and 7 would be the vector that is on the right hand side, and we will take an inverse of it, A inverse. So again, for A inverse, you should take a determinant, and while taking a determinant, if it is a linearly dependent row or column, or it will be 0, so then you can't find the A inverse, and you can find the value. So the value of x equal to 1, the value of y equal to 2. So similarly, like in our high school, we again like substitute and always cross verify. So we can always do that. You can see like we can get the RHS, that is 8 and 7. So that is what here it is, like 8 and 7. So the concept would be very similar, like for you for the 3 unknowns also. So again, like define it as a matrix, and then like have the right hand side the value as like vectors, and then like here, if you want, you can solve it through like linear algebra dot inverse, and then like use a dot product, or else the Python provides you a solution where you can directly use linear algebra dot solve to solve an equation, and the value of x equal to -1, y equal to 2, and then like z equal to 3, and you can always quickly cross check whatever value you got is the right one, for which you can always do the dot product and then substitute in the equation back and then get it. So here you can see like 1 minus 7 and 5. So that's what we have here, like 1 minus 7 and 5. So again, there are a few limitations in finding A inverse, because not all matrix has an A inverse. At the same time, if the matrix is singular, or like if it is not a full rank matrix, then the determinant is 0, then you can't find the A inverse. And similarly, the computational complexity of to find an A inverse is order of n cubed. So as the data set size grows, then like finding A inverse would be really hard. So let's take, if you have like 100 rows or like 200 rows or like 500 or like 1000, it's kind of fine, because as the data set size grows, the computational time would grows exponentially. So this is what like finding an A inverse will not be an optimal solution every time. So in your class, you will be seeing like what are the other solutions or what are the other methodologies that you can use apart from A inverse to solve the equation. So this will have this in the mind. So it will always like connect you once you are proceeding with the class. So the next one would be the norm of the vector. So here the norm is like the magnitude. Like if you want to find what is the length of the vector, or like what is the magnitude of the vector, so you can always use this formula. So here you can substitute p as 1. So to find the magnitude, so you always use the magnitude symbol of the vector. So here x is the vector and p is a real number. So p belongs to a real number, and it's always should be greater than or equal to 1. And if you add p equal to 1, so here it will be 1, here it will be 1. Then it will be a summation of the absolute value of the vector here. So let's take, you have this example as 4 minus 3. So just take the absolute of the all values, that is 4. So it will be 4 comma plus 3, because we are taking the absolute, and 4 plus 3, just as you do the summation, and you can always get the like 4 plus 3 is 7. So this is how you implement a norm in Python. And shortly you will be seeing like what is a real-time application in machine learning and how you will use those things in like machine learning exercise also. So similarly, you have norm 2, like when you substitute p equal to 2, so then it makes like square each and every element, and then take a square root of it. So here 1 by 2 becomes a square root of it. So square and sum the element and then take the square root. So that's how the formula would become. So here we have 4, then the 4 square is 16, and it's like 3 minus 3 square is 9. So when you add this both, it will be it will be like 25. Then the square root of 25 is 5. So that's what you are getting L2 norm as. So these are the cases for like vectors. Let's take if you have a matrix, then it's almost the same like it is again there is a form like it's called as another name is like Frobenius norm. It can also be called as Frobenius norm. So here let's take you have this matrix. So just take each and every element and then take a square of it and then to do the whole sum. So as per this like exact formula, take the square of each and every element, do the whole sum, and then like take the square root of it. So that's what like we will be doing, like whatever you are seeing here as an example. So Python has like again inbuilt functions that you can use like FRO. So when you use it, you can get the Frobenius norm. So we are defining the same matrix, whatever we have defined above, and then like FRO is the Frobenius norm, and then you can print it and you are getting the same value. So this norms would be like very helpful in regularizing a machine learning model. So again, like you will find like what is regularization, what is L1 regularization, L2 regularization, all those stuff in the upcoming class. So this is what the linear algebra concept that would be very helpful in a machine learning environment. So you will be seeing all those concepts even in the upcoming class. So just have in mind like whenever you are doing regularization, you will be using the norm of a vector or a matrix. So the next concept would be like a trace operator, where the summation of ai. So in the sense like the number of the row element, the column element should be the same, the position of. So if you take the trace of the matrix as 5, like because you just take the diagonal sum, so 3 plus 1 plus 1. So here like you get the trace of the matrix. I personally don't think like I've used trace of the operator, but like if people are who are like in math field or like who are already in like mathematical machine learning field, so they will obviously use it. So but I have an interesting proposal that you can always use is like try to use as much as inbuilt functions. So if you go into this page, so you can see like identity again, like that if you want all like this would be like really helpful. Like if you want like 5 ones, you can always use like np.ones of 5. So whenever you want to one-hot encoding or like all machine learning terminologies, so these concepts would be really useful. And then like you just see like you have a list of so many inbuilt functions. I would say like you don't need to mug up. You just have to like know few things, so that whenever you are using it, you can always refer it back, because these are like always open to come and refer for you guys. So another interesting example is like you can argue like always like, okay, I will use a for loop and then like take one element, and then like whenever the element is same, the row and column is same, then I will add it. Then also I can get the trace of the matrix. So you're 100% right. You can always do that. So let's see like how it affects in terms of runtime. So I am just using a normal for loop for a sum of numbers that we generally use. And this is an example where we use an inbuilt function. So you can see like when the runtime is like 7 seconds, and then like when you use an inbuilt function for same sum of numbers, it's like two seconds. You can see always it's like 3 times greater than you like the inbuilt function is always efficient to use. So whenever you know like in your code, if you can use an inbuilt function, so always go with an inbuilt function because that saves your runtime pretty good. So when you are working with like 10, 20 or like 100 examples or like 1,000 examples, you don't see a massive difference. So but when you are working with like large data set, like millions of data sets or like hundreds of thousands of data sets, so then like each and every small runtime also like matters. Let's take this is just like 3-4 lines. Just if you have like 1,000 line of Python programming and each and every line takes like 3 times more, then to run the whole program itself takes you a longer time to run. So any idea why the inbuilt functions are faster? It's because like they are implemented in the optimized way by default in the Python itself. So so it runs pretty quick. Like they use some sophisticated methodologies and makes the runtimes better. So that's where like it runs pretty quick. But the output or functionality would still be the same. And you can always like go to Python and then see like how they are implementing the inbuilt functions also, like if you want more idea about it. And So this would be the last concept today. So, and which is also a very important concept, like you will be using in again, like throughout the machine learning course. So let's take, so this is called eigen decomposition, where you find the eigenvalues and vectors, and A is a square matrix, and then like B is the vector, and the lambda is a scalar. So let's take this as a matrix, and then like you have -3, -2, 1, 0, and if you multiply that with 1, 1, you can always refactor that to like -2, 1, 1. So it's like, so here lambda is -2, and V is the vector, that is 1, 1, 1, 1, 1. So, and then like you can always multiply these two things to give you like LHS equal to RHS. So if you want just to quickly do it, you can always take the paint, and then like, so here you -3 plus 1, and then like here -2 plus 0. So you just multiply the scalar inside it. So it's -2, -2. So here it's like, again, like -3 plus 1 is -2, again -2. So if you can make a matrix decomposable into eigenvalues and eigenvectors, so we have to find what is the right lambda value, what is the right V value, that is the vector value. So here the official notation is like AV. So A is a matrix, V is a vector. So a dot product of matrix vector, if it is an equivalent to a scalar into vector, then V is the eigenvector and lambda is the eigenvalue. So then you can, if you want to solve it, you can always bring lambda V to the left hand side, and then like lambda, since it's a lambda is a scalar, you can always multiply with I, so that the shape of the matrix A and then the lambda would be same. And then since V is common, you can always take it outside. So if you want a non-trivial solution set, then the determinant of A minus lambda I should be equal to 0. So again, we can quickly confirm it, like why this value solution is exist. So here you can take A is as -3, -2, and then 1, 0, and minus, here the lambda value is -2, so which is multiplied by an identity matrix. So 0, -2. So then here you will get so minus will get like -3 plus 2. Here you get 1, and then like here you get -2 plus like again like -0, and then here you get -2, sorry, plus 2. Second. So here if you take so the matrix value would be like -1, 2, 1, -2. So then if you take the determinant of it, it's -2 plus 2. So then the determinant of the matrix is 0. So then that's why like you're getting a good solution for this. So this is an ideal case. So when if you want to implement that in Python, so we can again like declare a matrix and try to take the covariance of the matrix, because it encodes the correlation between each and every variable, and then like that helps you to solve the problem. So you get this value. So again, like we can always prove this value. So let's take, you got 3 eigenvalues, 1, 2, 3. So here, if the value is 7.3, then like an e power 0, so then it's like 7.3 really. And then like this eigenvalues is more meaningful and representable. So where we use eigenvalues is like, if you have thousands of columns, and then if you want just 100 columns, if you want to decompose it, if you want to decompose or reduce the dimensionality of the matrix, then we will use eigen decomposition. So if you rather than having 3 columns now, if you just want 1 column also, so if you just take the good column with a good eigenvalue, then you still have a good performance, though there would be a slight deviation between like if you use all the 3, and it's again a trade-off between the accuracy and the number of columns that you use. So these are the eigenvectors. So here it's like I'm taking 1, so it's like -0.6, and then like 0.75, 0.11177. So again, like we can quickly cross check with a matrix into vector equal to scalar into vector. So I'm taking A is the covariance matrix, and then I'm taking a dot product with the corresponding element, and then like I'm getting this value. So similarly, like you can do that on the right hand side, so you get the values as same. So this shows like it's perfectly solved and it is good. So if you just want to like make it as for a different eigenvalues and vectors, so you make it as 0, or like you can see like it's always the condition is satisfied, 0 and 2. So this is where the most variable lies. So it's like always, you can always quickly verify. Again, like if you really want to go in depth, like there's a good YouTube video also, you can always cross check it, because this is just like 45 to 50 minutes class. And then like you want to cover like a lot of topics. Again, linear algebra itself is a very big whole class with like multiple lectures. So it's like, I highly suggest like go to some YouTube lectures to even understand in depth. And then like let's see like the practical applications of machine learning. Like this is called a principal component analysis. So let's take, you have x-axis and then y-axis. So that is a plane. Generally, like you are in a two-dimensional space, and if you just want to bring it to a one-dimensional space, that is a line. So you just draw a line where the variability can be captured to the best, and then like try to compute the error. And then like now the green points are like the projection on the line, and then like now the two-dimensional plane is being represented as a single line, so that it resembles the same exact value as to the two-dimensional thing. So again, like this is called principal component analysis, and then you have a separate topic in our class itself as a syllabus. So but you will be using eigen decomposition in it, eigenvalues, vectors, and eigen decomposition in it. So this is a quick example for you. And then this is another good example. Again, like SVD is a singular value decomposition. So this is again slightly different from eigenvalue decomposition. Like if you see, like this is a full rank tiger. So we have already formalized what is a rank. So a full rank matrix, in the sense like it should be a non-singular matrix. That is like each and every columns or row should be like linearly independent from the other columns. So then it's like a full rank matrix. So then if from the full rank, now we are going to reduce it to 200 rank matrix. So still like it looks like a tiger. And similarly, now we again reduce it to 100 rank matrix. So now you will have only 100 columns of the tiger. Like when you convert a tiger image to a matrix, and then like now you have only 100 columns or rows, like you can still like see like the full rank is like kind of resemble to the 100 rank tiger. And then like again like 50 also still resembles the same, and like 30 is kind of okay, but 20 you can see like there is a quality loss. And then like 10 and 3 the whole image is lost, like you can't really find like whether that's a tiger or not. So it's like kind of a trade-off. Let's take, if the full rank matrix is like 500 cost 500, and you don't want to always use the full thing, because let's take for a single image itself it will take time to compute things. Let's take if you have millions of images and you slightly want to reduce the dimensionality of the image, and then like let's take for the whole image, it might give you like 95% of accuracy. But if you're using like rather than 500, you're going to use a 30 rank matrix, and that's going to give you like 93 or 92. So but still like that's a good trade-off that you're gonna get. Like in terms of runtime, you get like more than like 10 times or 15 times faster. So this is also another classic example that you will be using in machine learning. So you will use a 30 rank matrix, or like if you just want a slight improve in accuracy, again you can use a 50 rank matrix to get a better result. Again, like to point you a good resource, I have mentioned a good links here. So again, if you can go here, so you have all those things perfectly explained in a mathematical way: trace, norms, or what is orthogonality, what is determinant, and then like what is gradients of a matrix. So here you can see all those things written in it. And I would like to quickly add, like even in this Sarath's first lecture, we have seen solving linear regression problem. So first, initially, we thought of like using as a small notation, but then Sarath used like to convert that as a matrix and vectors, and then like he wrote in a matrix notation. So this is a standard practice that will be used in the upcoming algorithms, or like wherever you see a machine learning algorithm or like some implementation. So you always convert the idea into a matrix and a vector, and then try to see like how you can compute and then try to replicate it, because you don't need a for loop to iterate everything. So you can just use np.dot of a matrix and a vector, and then like within a short, like you can get computed the whole thing. So this massively improves your runtime, and it also increases your readability and then understandability of the code also. So again, like the second material I would like to point you is this is a like very like a Bible for like linear algebra. This professor is really amazing, and you can even go into in depth to get an intuition about like two-dimensional is a plane, and then like what happens during the determinant. When determinant is 0, what really happens. So there are like again like there are a lot of intuitive and in-depth concept. So if you really are very serious about career in machine learning, or like if you really want to understand, see ax equal to b, and then like a0 or ax equal to b. So I have like again like independence, bias. So it's like you go into like projection into a subspace. Subspace is like eigen decompositions, and then like eigenvalues, vectors, again diagonalization. So you have like whole series of lectures, and so again singular value. These are like advanced concepts. So you have like 35 lectures here. So which is like 1 hour each. So if you are like kind of like, if you want in-depth machine learning understanding, so always if you are really good at linear algebra, then it's like always good for you. Then you can always get the basic understanding of what's happening. So yeah, so this is my end of my tutorial on linear algebra and its practical application and Python implementation. So I will update this notebook with all the proper solutions, and then like you can always find it in the course website. So if you have any questions, like I can see in the chat, or like there is another 10 minutes we can discuss, or like I will be happy to help you if you have any questions also.
Thank you, Arjun, for the excellent tutorial. So guys, who has questions? Also, don't worry if you don't understand what is meant by PCA or regularization, because we haven't yet covered them in the lectures.
Exactly.
So they're gonna be covered. Don't worry if you don't understand. It's normal not to understand.
So this is like kind of a web series. So this is like first episode. So you have a lot of questions in the mind as you see the web series episode. So you will slowly understand the connection between like why we are talking about this. So because I just want to, because we learn linear algebra separately, but when we don't know like how it is practically implemented in machine learning, so then it's like really hard. So but if you understand like why we are using that, what is the intuition behind it, so even in the sleep of the night, like if we can wake you, and then like you will be still like know those concepts in depth. So that's what like idea is, like whatever topic we have covered, we have always associated with practical machine learning applications. So it will be like helpful for you. Okay, please can we have the last
Yes,
tutorial
you will
video?
have it. Yeah, we're gonna post it. Don't worry. We're going to do that. Like today, by today, you will see it on Moodle. Any other? You can also ask any question related to the course in general. You don't have to ask.
Yeah, you can be specific to linear algebra, but if you, what about assignment 0?
Assignment 0, I would prefer if you ask about assignment 0 in the office hours, which is today from 12 to 1 p.m. Yes. Do you guys use Piazza? Is everyone comfortable using Piazza or not? Because that is where you normally post your questions, or in the office hours as well. Does that mean no? Yeah, I'm not getting any response, but is it not easy to use Piazza? Okay. I think if there are no questions, we can just end the tutorial. And thanks everyone for coming. And thank you, Arjun.